Well, let's look at another coordinate system, namely cylindrical coordinates. And if you had a source of potential on an object that was cylindrical and that it extended to infinity in both directions, because of the cylindrical symmetry you'd have no phi dependence. The infinite extent along z gives you no z dependence, so you're only left with the radius dependence along the vector s. The first term of Laplace's equation in cylindrical coordinates, the one that has the derivatives with respect to s, is this equation right here. And so you go back to where I showed you the Laplacian in different coordinate systems. This is the cylindrical term in the first s position. So applying that then to a potential function that we're trying to find, because you have this equal to 0, you'll notice that if you multiply both sides by s, you get rid of this factor here, which is a little bit convenient. You multiply s on both sides. Then you're left with this derivative here equals 0, and so you've got a product in terms of taking this derivative here, and so the first derivative of s gives you 1, so that leaves you with delta v over delta s. And then the second term will give you s times the derivative of this quantity with respect to s, which is this quantity right here, and that equals 0. Putting that in terms of full derivatives, because this only depends on s, the partials are equal to the fulls, and so I can write it like this. We get a v prime of s plus s v double prime of s equals 0. So let's look at finding a solution to this equation, and we're going to do that before we apply the boundary conditions. We expect to get some arbitrary constants. So here's our equation. This is the one that we've derived. To solve it, we're going to let the first derivative of v with respect to s be a function of s, u of s. So substituting that in, here's our v prime of s, so that's u of s. V double prime of s is equal to the first derivative of u sub s, and then we have this times s, which is equal to 0. Solve for u prime of s, which is du ds, and you get minus 1 over s u of s. You can then separate this by bringing the u of s over here and the ds over here. So here's our u dependence over here, and here's our s dependence. So we integrate this side with respect to u, and we integrate this side with respect to s. So doing that, you can see we get logarithms. So the left-hand side is the log of u, and the second side is minus log of s plus a constant, cc. Well, if we represent this as the log of another constant, we'll have the summation of logs, where this has a minus sign. And so we can represent as a product the log of this C1, which is what we're going to call the log quantity here. So this is the log of C1 minus the log of S, which means the ratio of C1 divided by S. Okay, so now we've got the log of this quantity equaling the log of this quantity, which means this quantity equals this quantity. And so that's what we have here. U of S is equal to C1 divided by S. Well, remember what this is. This is the first derivative of v, so we just plug that in. Here's our dv ds, and that's equal to the right-hand side C1 over S. We can integrate that again, so we have dv of S equaling C1 ds over S. Taking the integral of this side, we get v of S. The integral of this side, we get C1 times log of S, and we lump the constants that we would get from both sides into this C2. This is the solution with the arbitrary constants for Laplace's equation, where we have not yet given the boundary conditions. So let's go back to Mathematica and take a look at what this might look like. Here's where we left off with the Cartesian coordinates. Now we're going to go to cylindrical. We've already said that this is what the Laplacian looks like, and when we simplify that, we get this expression here. Let's first do the solution without any boundary conditions, and so that's the same thing we did before. We now write the full differential equation, this thing right here, equaling 0. We don't give boundary conditions, so Mathematica says put in this for the function and this for the variable. There's some other steps in here, but it's just show and tell. So here's what we get. One-dimensional cylindrical solution, no boundary conditions, is the same thing we got by hand. Constant C2 plus C1 times the log of S. We could try to do what we did before. We could put in the boundary conditions, setting S equal to S1, S equal to S2 with the voltages here. But it's easier just to do the whole thing with Mathematica. So here's dsolve, and we start with the curly brackets giving the function, one boundary condition, and then another boundary condition. This is the function that we're trying to solve for, and this is the variable. Here's the result. It's a little messier than the other case for the Cartesian, but it's still here. Here's the place where you have the variables. So you could factor out v1 minus v2 times log of s. Then the rest of it is a constant that has all of the different quantities. It has v2, it has v1, it has s1, s2. So you can see then that you get an expression that looks like a constant times log of s plus another constant. So it has the same form, but now we know what those constants are. Okay, so as we did before, we're going to take two values of s. S1, I'm going to set it equal to 1 because I can't let that go to 0. The reason being is that log of s goes to minus infinity at 0. So I have to keep this away from 0. I can put 0.001 or whatever I wish there, but I just can't let it go to 0. So we'll take 1 and we'll take S2 equal to 10. Here's our plot. This is the same function as right here, so that's what we're going to plot. So it shows us the similar format. Now it's just plotting from s equal 1 to s equal 10, which is what we asked it to do. The two potentials are still equal. They're minus 5, and so we get this straight line because there's no difference between the two potentials of the positions. So now let me take v2 and take it up to plus 5. So we're at minus 5 here, plus 5 here. You might want to see what it looks like when this is grounded. Let's take this one to 0. This one is at 0. This one's at plus 5. So it's just common to do. You ground the inside. This is basically a cylindrical capacitor. So there's a surface with radius 1 surrounded by a symmetric cylinder at s equal 10, and this has a plus 5 volts applied to it, and this one is grounded. So this is the resulting curve that you would get for that particular case. What happens if you take the electrode here and change the voltage? Well, if you go to 0, you get the straight line because there's no potential difference. And then as you go more negative, it has this curvature here, which takes you from the inner cylinder to the outer cylinder like that. And then you can say, well, what happens if I put plus 5? If you wish, now you're going from plus 5 to minus 5, and it just extends that curve like that. So this is then the solution of the cylindrical capacitor, actually, because we have voltages that are applied symmetrically about the axis of symmetry. This cylinder is at radius 10. Right now it's at minus 5 volts. This one's at a radius of 1, and it's at plus 5 volts. Remember, we have no max or min. You can see that it has no max or min except at the endpoints. And just to bring that home, let's switch. See, there's no maximum in this region here. There's no minimum except at the endpoints. And then the second thing is if you go to a point and just take a small differential on both sides, this would be approximately true. So if you make d small, it does in fact hold. I just wanted to show you what this equation looks like when you put it into sort of normal variables. So you let this inner radius be a and the outer radius be b, and I end up then with the s dependence right here, which is the log of the outer radius divided by s, and then it's divided by the log of the ratio of those two radii. And then that's times v0, which is the difference of potential between the two cylinders, then has this form, which is the more common one that you see in textbooks. So let's take a look at Laplace's equation in spherical coordinates where we have no theta or phi dependence. So we're only going to have results that depend on r. Here we have the Laplacian in spherical coordinates, and we have somewhat the similar case that we have this factor here. If we multiply by r squared, we can get rid of this factor because we have a 0 over here. Because this is one-dimensional, we can replace the partials with full derivatives. This is what we get. So this is the resulting differential equation of the Laplacian in spherical coordinates, and you'll see that it has a 2 times r v prime of r plus r squared v double prime r equals 0. Well, the solution can be found the same way. You let the first derivative of v be a function, substitute that in, and then do all the integration and separation. And so you end up with a similar result where you have the log of u of r equaling the log of a constant, and this time divided by r squared. So this is your resulting function with a arbitrary constant c1. And remember how we got that. We took cc and said it was log of c1, and that's how we ended up with this expression. Well, this is the first derivative of v with respect to r. This is u of r equal to c1 over r squared. Separate that and integrate, and so you'd have this expression here times this. And so when you integrate that, you'll get another constant of integration. This will come out as a minus 1 over r, and so just rewriting it then, your v of r, before we use boundary conditions, has 2 arbitrary constants, and the term that's r dependent is minus constant over r. So let's go to m again, and here's our Laplacian. This is after we take those derivatives, and this is the resulting differential equation. So this time I wrote it in terms of the Mathematica notation for that derivative with respect to r, and here we're solving the dE. So this right here is just this equation, this one right here. We're solving for v, and the variable is r. We get exactly what we had before. We get minus a constant over r plus another constant. So we're getting the same type of result that we did by hand. Let's put in the boundary conditions, which are exactly the same as we had before, namely that if we go to r1, we get v1. If we go to r2, we get v2. And again, this is a spherical capacitor. Here's the solution where we put in the boundary conditions. So here's our dE. Here's our first boundary condition. Here's our second boundary condition. We're solving for v, and the variable is r. So here's the solution. So this is the general solution with the boundary conditions. It's a spherical capacitor. The results are right here. Here's the r dependence right here. There's an r here. There's an r here, which you could bring together if you wish. And there's an r down here. When you put all that together, you're going to get an expression that looks like this, where now C1 and C2 are defined in terms of R1, V1, R2, V2. And I'll try to show you what that looks like later. So just for now, this is the solution, and so now we want to see what this does when we change the boundary conditions. So again, I set the inner sphere at a radius 1 and the outer sphere radius 10. So those are like the cylinder values that I showed you. Here's the resulting plot, and we start with these two equal, and I just use the same values. So I have minus v1 and minus v2 at minus 5, minus 5, and so that's what we have here. So this is the inner radius, this is the outer radius. So let's do the same thing. We bring this up. It has a different curvature, but it looks similar to the cylindrical capacitor. Here it's a 1 over r dependence. There it was a logarithmic dependence. And the same thing goes here, that if you bring this up to the equal, you get a straight line. If you bring this down, you get a curve that looks like this. If you put this at 0, like that, then that would be grounding the inner conductor and putting a minus voltage on the outer conductor. Or if we go positive, then it looks like this. By manipulation, we can see what this potential curve looks like for all the different starting and end points. So once you have the equation solved, it's the boundary conditions that determine this curve. There's nothing else you can change unless you want to change the size of the system. By wiggling these, you can get the values you want, and if you don't like my values, well, you just go up here and change them right here. So if you want to go from different potentials, you can change that. Just as we saw before, so here we're starting with a negative voltage inside going to positive. We don't see any max or min between the two endpoints. If we take a point at any point in between and take a small interval plus minus d, then we have the averaging effect for finding the point at v equals r. So if we're here and we go this way and this way, take those two endpoints, average them, we'll get the value of the potential. And because of the curvature, you have to make d small for this to hold. Let's go back to this normal notation. In that case, we'll let R1 be A, R2 be B, and let A be smaller than B. V1 we'll call V0, and we'll ground V2. If you do that, make the substitutions, run this, this is what you get, and then by hand I put it into this form here. So looking at this, you'll have a term that has a 1 over r dependence, so this part of the numerator divided by this is a 1 over r dependence, and then when you take the second term, you have an r divided by r, so that'll give you a constant expression. So it's a 1 over r dependence plus a constant.